Okay, so let's start. Okay, so hello and welcome everyone to the sixth lecture of our CUDA programming. So in the previous lecture, we saw, like in the previous lecture, we saw how is the GPU computation hierarchies. We also saw a typical matrix querying application. In the previous lecture, we tried to parallelize that application by parallelizing the two outermost loop of that matrix querying CPU application. Then we also saw how to launch the kernel when the data size is very large, and we saw two issues that we can typically face when we launch the kernel with huge data size. Then we delved deeper into the warp, what is warp and all those stuffs. Then we also briefly looked at what is the thread block and all those things, and what are the advantages of having thread blocks. Like there is something called as fast synchronization and fast scratchpad memory or shared memory available for the thread block. Then we saw what is warp, how the warp executes. We saw that the warp executes in SIMD fashion, which is single instruction multiple data fashion, and it executes in a lockstep manner. Um, then we typically looked into the uh, issue that warp-based execution can have, which is the thread divergence issue. And there we stopped yesterday. So that was the brief outline of the outline of the last lecture. For the today's lecture, we are planning to delve deeper into the thread divergence issue. We'll see a couple of more examples for this thread divergence issue. We also see how to mitigate, how to remove the thread divergence step by step for a few of the sample programs. Then, at the end we'll start a new topic, which is memory. Till now we have been looking computation aspects of the GPU. Now we'll start with the memory aspect of the GPU at the end of the lecture. So we'll briefly touch upon the memory aspects. We'll see how the memory is organized and all those things we'll see. And probably there will end. We'll not delve deeper into it. Like we'll not delve into locality and latency principles and all those things. But yeah, we'll just see the organization of the memory and GPU, and there will end for today. So that's the brief outline for the today's lecture. Uh, okay, so with this, let's get started for the today's lecture, which is the sixth lecture. Yeah, so as you can see on the screen, this was the last slide where we left off last time, right? I mean, not left off, but this was one of the slide that we saw in the last lecture. So if you remember, I told that, if you remember, I told that we have this kernel named as D kernel, and we have this vector of size 32. Vector, which is of vector size, not 32. But we are launching this kernel with 32 threads, and which is one warp. And this is the way the ID is computed using this equation. And ID will go from 0 to 31 as there are 32 threads. And then we saw that as there are as the id as the id of the thread can be either even or odd. If the id of the thread is odd, it will execute the statement as one, and if the id of the thread is even, it will execute the statement as two. So the statement s0 will be executed by all the warp threads, but s1 will be executed by odd id threads, and s2 will be executed by even id threads, and then again s3 will be executed by all the threads. So you can see here as it is shown here. So if you observe it closely, you will be able to observe that the number of steps taken by warp threads to execute this if-else construct is 2, right? No matter whatever warp thread you pick up, the number of steps taken by that warp thread to execute this if-else construct is 2. So you can see for thread with ID 1, it takes 2 steps. For thread with ID 0, it takes 2 steps, and so on for any whatever ID you among the warp threads. So that is the one point that you should note here. For this if-else construct, the number of steps taken by warp threads to execute this construct is 2. Yeah. So with this, please keep a note of this, and with this we'll move forward for the today's lecture. Now I have a small classwork for you people. This is a slight variation of the example that we saw in the previous lecture. But, let us do this. So for this code, for this piece of code, I have 2 questions for you people. First question is, how many steps will the warp threads take to execute this if else construct? Again, how many steps will the warp threads take to execute this if else construct? Assuming that there are only 32 threads, that is one warp is there, and how many steps will be taken for the execution of this if else construct? And second question is, how can we I mean, we know that this code diverges, right? Because in worst case, 32 threads, some threads might be executing this, some might be executing, for some thread, this condition might be true, for others, this might be true, and for rest of them, this else branch might be the case. So, in worst case, all these three, threads can go in either of these three conditions. So, I want each and every one of you to answer how many steps in worst case the warp threads can take to execute this construct, and how can we remove this thread divergence is the second question. How can we remove the thread divergence from this piece of code? So I'll stop here for some seconds and we'll wait for you people to answer either by unmuting or by writing your answers in the chat. I hope that question is clear. Please try out and post your answer in chat. Okay. Okay, I'll switch to the chat to see what you people are typing. Okay, 3 steps worst case, yes. So I request you to try out for the second question that I asked. How can we remove the divergence? Yeah, good evening. Yeah, I'll switch back to the slide in case anyone wants to look at the question again. So this is the question. We want to remove the divergence. First question is how many steps will it take for warp threads to execute, and second is we want to remove the divergence. So please try out. I'll wait for a few more seconds. Okay, I'm switching back to the chat. Okay, cool. I can see some responses. 3 steps, 4 steps. Okay, 4 steps is saying someone is saying 4 steps. Yeah, this equation looks okay to me. Z 5 plus z plus w minus x. Yes, similar to the last question. Yeah, that is correct. I guess this equation is correct. But how can it be 4 steps? As I'm wondering. Just don't include that assert statement. Without assert, it's 3 statements. 3 steps, I guess. Okay, so let us understand it. I'm happy that you people have tried, but yeah, so let's move to the slides and understand how is it working. So okay, so let's try understanding it. So first of all, for those who haven't understood it, so like it will take 3 steps to execute this if else clause or construct. So as I told, in worst case, it might happen that warp threads, which is bunch of 32 threads, might go into different conditions. So let's say for first 5 threads, this condition was true. So they'll execute this statement, the rest all will execute no. Then let's assume that for 6 to 15 threads, this condition was true. So they'll execute this condition, this statement, and for all of else for everyone, I mean for all other threads, they'll execute no op. And let's say for threads from 16 to 31, yeah, so assuming that thread ID goes from 0 to 31, from 16 to 31 threads, this else, they fall in this else condition, and this statement was executed, and rest all of them execute no op. So in worst case, 3 steps will be taken, right? Yeah, so 3 steps can be taken in worst case. But let us say we want to tweak this code in such a manner that we want no divergence. I mean, we just want to finish this thing in just one step. Then how can we do it? As some of you pointed out, we can simply use this formula. As we know that either, I mean, x can either take the value of y, z, or w. So there are again 3 cases here. So we can just replace this entire if else by this one statement. And is this correct? So as I explained in the previous example, let us analyze this case by case. Let's say the value of x was equals to y. Then in that case, this value of y. So how this right hand side of this equation will evaluate? This y and this x will cancel out, and this right hand side will turn out to be z plus w, which is actually what we want when x equals to y. That is case 1. Now case 2, when x equals to z, in that case what will happen, this z, how the RHS will evaluate, how the RHS will look, this z and this x will cancel out, and we'll left up with y plus w, which is what we want in that case when x equals to z. And in third case, when x equals to w, this RHS would evaluate to, this w and x will cancel out, and RHS would evaluate to y plus z, which is what we want when we fall in that else part, which is x equals to w. So this one will exactly, I mean, serve our purpose, because it is similar to this entire if else class. Okay, I guess everyone got this point. If there is any doubt here, then I'll probably wait for a second and move to chat to see if anyone have any quick question.
Yeah, I had a quick question as you were
Yeah, yeah.
saying the number of steps. So, in the number of steps, you said not to include the assert statement. Is that?
Yeah, yeah. I mean, I was like, how many steps does it take for warp threads to execute this if else clause? So assert is not part of that if else.
Oh,
So question was that, I mean, I didn't told that what is the number of steps taken by warp threads to execute this entire fragment. That was not the question. The question was how many steps will the warp threads take to execute this if else clause or construct. So that answer is 3. But if we consider this assert also, then the answer is 4. That is correct. Yeah, but for this part it's just 3. Okay, I hope that's clear. Quickly,
yes.
I think that there are no questions. Okay. Okay, then let's move on to our discussion further. So this was like a warm-up question. We'll see more involving questions further. So let us start with a very good exercise now. Let us say that we have let us say that we have this kernel named as t kernel, which is taking 2 arguments, which is one is the pointer to the vector, which is again pointing to some GPU memory location. Vector size is the size of the vector. Now, as we saw in the previous lecture, this ID is the, I mean, this equation calculates the ID. And let us assume that this kernel is launched with 1 watt, which is 32 threads. And okay, so 32 threads are there. So ID will go from 0 to 31. And then we have this if else if construct, if we can observe here, this entire if else if. So again, my question is simple. How many steps does the warp threads take to execute this if else if construct? Just this if else if construct. Don't include this ID calculation always. Just focus on this if else if. How many steps will warp threads will take to execute this if else if construct? So I'll pause here for some seconds and we'll wait for this time. Then we'll move on. Okay, so one thing that I want to mention here is that assume that this uh, I mean this loop thing doesn't affect much. So if there are 100 iterations here, assume that each iteration takes one step and loop doesn't count towards a steps or anything. Please consider it in that way. So for this loop, consider it as 100 steps because we are going from 1 to 100, right? So consider this loop as 100 steps. Keeping that in mind, how many steps will, this entire if else construct will take? So I'll wait here for a few more seconds and then we'll probably go to chat and then check it. Okay, let me go back to the chat. Okay. Santa is saying 2, worst case 2, but mostly 1. Okay, why people are telling 2? I am not able to understand 2. Worst case 100. Yeah, this seems quite reasonable. Worst case 102 steps. 1. I don't understand why 1. 1 is like 1 will be when there is no divergence or something. Okay, 100. Okay, 101. So please think about it. Request each and every one of you to try and switch back to this slide so that you people can try. Please think about it. Unless you try, you want to be, it will be difficult. Okay, let me go back to the chat. For ID, 1 steps shouldn't if the condition be out. Okay, let us see. What will happen? Someone is saying 102. Okay, that's good that many of you have at least tried. That's good. So let us understand what will happen. Uh, okay, let us understand what will happen. As I told, this kernel is launched with exactly one war. So there are 32 threads and ID will go from 0 to 31. Correct? So now what will happen? Let us try to analyze this. So let's say all the thread comes here at this if condition. They'll see that only one thread which has ID 0 satisfy this condition because for only thread with ID 0, 0 is less than or equals to 0 is true. For all other threads, ID is 1 from 1 to 31. So this condition will be false because from 1 to 31 is a positive number and it's not less than or equals to 0. So for all other threads from 1 to 31, they will never enter inside this if condition. They'll enter inside this else condition. So currently only one thread has entered inside this if condition. Okay, and that one thread which is having ID 0, it's executing how many steps? Let's try to understand. It is executing this step which is one step. Then this 100 steps of this for loop. So total 101 steps are being executed by the thread which is having ID 0. So okay, so thread with ID 0 is executing 101 steps here. Meanwhile, what these other threads are doing, other threads which are having ID from 1 to 31, what they are doing? They are just executing norm, right? So threads with ID 0 to, thread with ID 0 has executed 101 steps and all other are executing norm. Okay, so that's fine. And once that 0 thread has finished, all the threads will come in this else part. Now for this else part, thread 0 will not enter this else part. So all other 31 threads will enter having ID from 1 to 31 and they'll execute this statement which is vector of ID equals to 1. that is they are initializing that particular memory location with 1, and all threads from 1 to 31 ID will do this step, and 0 thread will execute no arm. So total how many steps are being executed here? 101 here, and then 1 here. So 101 plus 1, which is 102 total steps are being executed. If you observe carefully, total 102 steps are being executed by the warp threads. So that's the answer. If you have any question, then I'll quickly go back to the chat, otherwise we'll move further. 102, yeah, 102 is correct. 132, I didn't understand.
Sorry, typo.
102, okay. Okay, if there is any doubt, I'll pause here for probably 4-5 seconds or yeah. Okay, if there is no doubt, let's move further with our discussion. Okay, so we understood that this if-else construct takes 102 steps for warp threads to execute. Now, again, my question is that can we improve this? Can we reduce this 102 steps to, let's say, lesser steps? Let's say from 102, can we reduce it to 50 or something like that? Can we do that, or even lesser? So I hope that you got my question. So this if-else construct takes 102 steps for warp threads. Can we reduce it to some lesser steps? So I want each and every one of you to think about it. How can we do that? And yeah, I'll stop here for a couple of seconds or probably a minute for you people to think, and then we'll discuss the solution.
Of this mass.
Okay, let me go back to the chat. Yes, I think that is correct. We can do this thing. 9 plus 1 by 2. Yes, I think both of you are correct. I also request others to try so that you can practice out of it. Okay, but yeah, I think the answer is correct. So let's move on. Uh, okay, so in order to, okay, for others, I'm just explaining it in some better manner. So in order to understand how can we reduce the steps further, we need to understand what uh, this if condition, what is the statements inside this if condition. First thing is that the most expensive part is this thing, right? Because from 1 to 31 threads, which are, the threads having 1 to 31 ID, they are just taking 1 steps. But the main bottleneck is the thread 0, which is taking 101 steps. So is there any way we can reduce this one to just few steps, or let's say 1 step? To do that, we need to understand what is happening here actually. So if you see, what we are doing is we are initializing the zeroth memory location because ID is 0. So we are initializing zeroth memory location to 0, and then what we are doing is just sum of first and natural numbers, which is yeah, I is ranging from 1 to 100. So we are doing sum of first 100 natural number and placing it at the 0th memory location. So yeah, so I mean the idea is simple. If we can just remove all these things, this loop things and all those things, and just replace it by the formula of first and natural numbers, in this case first 100 natural numbers, it will reduce the number of steps, and this is how it can be done. Uh, for if the id is less than or equals to 0, then we just simply do vector of id equals to 101 into 100 by 2, which will simply calculate this thing only, this entire thing only, and this can be done in just one step, right? So yeah, so this will reduce the number of steps, and here we just keep the same thing that we had previously, if you see here. Yeah, so this and this thing are similar. So okay, so it seems like we have reduced the number of steps. So like I request request you to try out how many steps does it takes to execute now. It will be very quick. I mean, you will be able to tell it very quickly how many steps this if else if construct takes to execute now for the warp threads. Quickly, go to the chat. Yeah, 2, right? Yeah, obvious. I mean, everyone would be now able to guess like it's 2. Okay, so that's good. We have reduced. Okay, I'll quickly move back to the slides. Okay, I'll quickly move back to the slides. So number of steps taken for this, this if else if construct to execute for warp threads is 2. Now again, it still takes 2 steps, and there is still divergence here. I mean, threads are diverging, right? So I mean, because first thread is first thread will execute this part and all other will wait, and all other will execute this part and first thread, 0th thread will wait here. So still, if you see, there is a thread divergence here. So I request each and every one of you to try further. How can we reduce the thread divergence further, or how can we reduce the steps further? Here, 2 steps are needed, right, for the warp threads. Can we reduce it to just 1 step as we did here, if you remember? Yeah, here, right? We just reduce this entire 3 steps to 1 step, right? So can something like this be done here? Can I request each and every one of you to try out this and post your answers in the chat. I'll probably wait for a minute or probably 2 minutes to think. Wait for you to think about, and yeah, then we'll proceed.
question 0 कैसे निकालो
Was there any question? Someone was speaking, I guess. Okay, Gokul has typed something. He's saying vector of id equals to 1 and then vector of 0 equals to 101 into 100 by 2. Okay, I'll ask you a question here. How many steps it will take? Yeah, it's 2, right? Still it's 2 steps. So it's, we have avoided if else if here, but we should think in a better way, smart way. Think smartly. Can we reduce it to just 1 step? This is my question. Yeah, please try. If you are unable to find the correct answer, that's okay, but please try. I'll switch to the slide again. I'll wait for a few more seconds because it might not be very straightforward. So I want to give you people some time.
One.
I mean, I heard someone speaking. Okay, Varun has typed something. Let us see what he is telling. Okay, will this work? What is this ID less than 0? What does it does? I mean, okay. Yeah, I guess this should work. This is one of the way it can be done. But yeah, I have proposed something else. But let us see. I mean, yeah, this seems correct to me. 101 into 100 by 2 minus 1. And yeah. One of the way it can be done is this. Yeah, correct. Varun has probably given the correct answer. But I think there should not be 1 here, right? Because ID less than or equals to 0 will evaluate to true for 0th thread, and that will cancel out this 1. So why are you placing this additional 1 here? And
so in case of 0, we want 101 into 100 by 2, right?
yes,
So the 1 will cancel out,
yes,
which is needed. And in case
yes.
of other values, id less than equal to 0 is 0, its true value, and multiplying it with it, the answer will be 1, right?
Okay, I got it. This is multiplication. Okay, this one is okay. Got it. Yeah, got it. Yeah, I think this looks correct to me. Request others to also try. Okay, yeah, typecasting. I mean, it's good to typecast. That is correct. Okay, looks good to me. Then Gokul is saying value to divide by value minus 1 into ID plus 1. Okay, but ID will go from 1 to 31. So you need to do something like this, the way Varun has done. Because you should be able to generate a mapping in such a way that if ID is 0, then it will give 1. Else, if ID is positive, then it should be able to give you 0. So I guess this should not work. But anyways, I mean, it's good to try. I mean, it's good that you have tried. Okay, so I think I've given even enough time. Let's get back to our slides. So, okay, so one of the way it can be done, I mean, the way I thought was this. If you see, there are two important observations here. First is that ID is going from, if you see this equation, we are computing ID, and ID is going from 0 to 31. And ID can either be a 0 or can be a positive number. That's one observation. Observation number 1, that ID can either be 0 or can be a positive number. And second observation is that ID is an integer, so it takes 32 bits. I mean, in memory it has 32 bits, where the specific bits are from 0 to 31, right? The way the integer is declared is there are 32 bits reserved for it. So the way that I thought of doing it was like this. When you have a number, integer number, and it's a positive number, in our case it will be a positive number or a zero. So when it is a positive number and you negate that number, then if you people know, its sign bit, positive number as sign bit as 0. When you negate it, its sign bit become 1. And when you shift that negative number which has sign bit as 1 by 31 times, what will happen is sign shifting will happen. I mean, sign will be shifted, and every bit will become 1, or sign copying will be done, something like that will happen. So all 32 bits will become 1. Uh, so like if the number is positive, and if you do this thing, this minus id left shifted by 31 times, sorry, right shifted by 31 times, and if the number is positive, it will become all ones. And if you people know, all ones in 2's complement is actually the -1. So if the number is positive, and if the number is positive, what will be the output of this equation? It will be -1. So when the number is positive, this thing will emit -1, and -1 plus 1 plus -1 is 0. So for positive numbers, this entire thing will become 0, and when the number is 0, this entire thing will become 0, because no, I mean, if you do -0, the number is still 0, and sign bit will remain 0, and when you shift it by 31, the entire number will become 0. So for 0, 1 plus 0 will happen, which is 1. And yeah, so the key point to remember here is this entire thing will evaluate to 1 if the number is 0, and 0 if the number is positive. So in our case, when the id is 0, this entire thing will be 1. 1 into this entire thing will be again this entire thing, 101 into 100 by 2 minus 1, and plus 1 we are doing. So when the id is 0, we'll get this thing, 101 into 100 by 2. And when the id is a positive number, this entire thing will be 0, as I explained, and 0 into anything is 0. And so what will be left of is this just 1, this 1, and that 1 will be assigned. So this is exactly what we want. This id, vector of id, is this thing when the number when the id is 0, and when it is positive, we want this 1 to be assigned, and that is what will happen here. And the cool thing to observe here is that we started off with this thing, this entire thing, and it took actually 102 steps to execute for warp threads, and we have just reduced it to just one step, if we can see here. So I mean, yeah, I mean, so number of steps the warp threads will take to execute this one is now just 1, and we reduce it from 102 to 1. And yeah, so the key takeaway from this example or this exercise is that in many of the cases, if you see the computation properly, you will be able to reduce the thread divergence, and it is possible in many cases. But there are cases where you won't be able to reduce the thread divergence, especially in graph algorithms, mostly when the computation is irregular and just can't avoid the divergence there. But in many cases, like this is one of the examples where you can reduce it from very large extent, I mean from 102 to just 1. So yeah, please make a note of it, that in many cases that is possible. Okay, so if anyone have any doubt in this slide, I'll just quickly go to the chat and oh, because it's negative, it will always shift to 1. Oh, so okay, when the number is negative, the sign bit is 1, and I mean, sign bit is the most significant bit in that 32-bit 32-bit number, and that bit will be shifted, and the entire, I mean, it will be not shifted, but it will be copied in consecutive bits. So entire 32 bits will become 1 1 1 1, and that number with all ones in the 32-bit is actually -1. If you know the 2's complement, or I mean how the 2's complement work, that the number with all ones in it is actually represented as -1 in 2's complement representation. So okay, next question is not of id and 0, would this work too? ID and 0. Let me think. Okay, you are saying that wait no ID and 1. Okay. Yes, please. Please go ahead. Your voice is breaking. Can you speak again? Hello. Okay. So let me think about this ID and 1. Okay, but how are you planning to do this? I mean, you should give the entire equation. ID and 1 will give 0 when ID is 0. And in rest of the case, it will give 1.
But actually, it will give one on all also if it is an odd number, right? I think.
Yes, in every case, it will, I mean, for positive number, I think it will give 1 for all the positive number. ID
Oh,
and 1.
numbers it is 0.
For 0, it will give 0. Because
Even number,
this is bitwise AND, right?
but the even numbers in that case.
Yeah, for even numbers, it will not give because let's say number is 2, then it's 1 0, and 1 and 1 0 will give 0. So your equation might fail for even number if you are planning to use this as something like here multiplication or somewhere for the multiplication. Then for even number also it will give 0. For odd number it will give 1. So yeah, it highly depends the way you are using it. I mean, how you are framing the equation. So yeah, so please try out. I mean, it might work if you place it properly, is what my suggestion. Okay, anyways, let's move further from here. So again, let us continue our discussion with thread divergence. Let us say that I have again one more kernel which has the name again D kernel, and again there is this vector and vector which is the array which is allocated on GPU pointed by this pointer vector, and the vector size is the size of vector, and then again we are calculating the ID in very conventional manner, and we are launching this kernel with again one warp, and which is 32 threads, and ID goes from 0 to 31, and we have this switch case construct, and I want you people to tell me how many steps will warp threads take to execute this switch case, this entire thing, entire switch. So I'll wait here for a few seconds and for you people to try out how many steps it will take, and then we'll probably move on with the discussion. Okay, I think someone said 10. 1, how can it be 1? Can you, I mean, can you explain? Someone is saying 2. How can it be
If
2?
switch condition is, then it will execute that statement.
Okay, I'm talking about entire warp. So like, okay, let me go back to the uh, slide. I mean, so warp has 32 threads, and ID of those 32 threads range from 0 to 31, and based on ID we are switching, right? So it's very much similar to writing that if else ladder, if you remember. So I don't think that it will just execute in one step, but yeah, let us see. I mean, someone is saying 2. 2 steps. I request you people to add the explanation also, otherwise how can how can I understand how, the way it is working, 2 steps. Probably you can unmute yourself and okay, so executing a case is like you are going inside a let's say if you it's very similar to if else. So switch case is very similar to if else. So let's say if your condition is true. So okay, in fact let me explain it with that slide itself. So I'm happy that you people have at least tried, but let's understand this, or at least let us see what I think about it. You people might be correct, but I need some convincing explanation so that I can digest the thing. So okay, but let us understand it with this slide, at least what I think about it. So uh, okay, yeah, so id ranges from 0 to 31, and then we have this switch statement, which is switching based on the id. So id can range from 0 to 31, right, as we know. And based on the case, the thread will execute that statement. So for the thread with id 0, what will happen is that okay, so this first of all, this switch is executed by each and every thread, right? So what will happen is thread with id 0 will go inside here, and it will execute this statement because case 0 is true for it. And for all the rest of the threads, what will happen is they'll execute no op. So one step here, thread 0 is executing here, and all other threads are executing no op. For a thread with id 1, this case is true, so it will execute this statement. All others will execute no op, and this will go on. This will go on till 9. For ninth thread, this case 9 will, it will evaluate to true, and it will execute this statement. Okay, and the rest all will be executing no op. So in worst case, 10 steps will be taken because there are 10 cases. Consider it as a if else ladder. Like it is as good as writing if id equals to 0, then do this. If id equals to 1, then do this. If id equals to 2, then do this, and so on. If id equals to 9, then do this. If I just replace that thing by this, I believe that the number of steps taken are 10 for the warp threads. If there are any question, or if you feel that something was wrong, then please unmute or just type in the chat so I can also.
So I have a question there.
Yeah, please go ahead.
So when case 0 executes and it fails and it goes ahead and eventually case 9 also executes. So there are total 10 counting from case 0 to case 9, including the statement for case 9 as well, right? So won't there be 11? Like to execute the statement for case 9, which is about the statement that's being a
Okay,
vector ID 9.
I didn't got it. Which one you are telling? Just can you reiterate that?
In case of case 9,
Okay.
you even the statement of case 9 needs to be executed, right? And along with actually verifying that it is a case 9.
Oh, okay. Yeah, you are telling that you need to check that if it's a 9 or not. The ID is 9 or not.
Right.
Okay. Yeah, that can be included. But so far, if you remember in our all the previous examples, if you see here, we are not including that as a step. Well, it can be included as a step, but when I say a step, uh, I'm talking about this basic block. Or let us not talk about basic block now, but I'm talking about this thing. The statements which are inside this clause. This thing. Inside this curly braces. So in this similar way, I am not counting this case checking as a. I'm not counting this case checking as a step.
In
Yeah.
that
So
case, I'm a little confused. Could you go back to one of the easier examples and explain how it is true? Or
yeah. So okay, let us do this thing only. This is the most simplest one. So here we also have this timeline, right? So here I'm not taking this if thing, checking this if condition as a step. I'm just taking this one as a step, like execution of this statement and this statement as a step. So you can see that this is one statement. Then there is no op for all other three. Then there is this statement. I mean,
Okay, no
excuse.
is a closure. Okay, understood.
So in that way, if you take, so I mean, this is very similar to if else, right? If id is 0, then do this. If id is 1, then do this. And if that is the case, we are not taking id checking as a step. Is what at least that is the way I'm thinking. Yeah, but if you are thinking in that id checking way, then it might be more steps. But the way I'm thinking, it will take 10 steps exactly. Any more confusion? Please can type it in chat or just unmute and ask. So verification. Yeah, that is correct. If we look deep enough, then we can say that verification is one step and go to line is another step, then expression another. But that is, if you are really planning to go deeply Gokul, then if you say this, how this switch case and all those things and if else condition are written in uh, very low level language, it's go to, right? It's go to this step and all those things. So yeah, you can consider it as a step, but just for the sake of simplicity, I'm not considering it as a step. I mean, to make the discussion simple. Yeah, but I agree that if you want to consider it as a step, then you can. Okay. I guess we just need to look at lines of code. The thread is in. Yeah, that is what I am focusing on. Yeah, okay. So let us move on to our discussion. Okay, so as we know that this will take 10 steps, not considering the checking as the step, this will take 10 steps to execute for the work threads. Now I want you people to think about how can we reduce this as we did in our previous examples. How can we reduce this 10 steps to probably lesser steps? Please think about it. I'll give few seconds here. Wait for a few seconds here for you people to think and post your answers in the chat.
I have a question.
Yeah, this one. Yeah.
What is the initial value of vector ID, like, or what is the initial value of vector?
You can assume that it's a garbage value. I mean, we haven't initialized it, right? So,
So, like,
assume
for
that.
example, case 3, it goes to vector of ID plus 3, which will be vector of 6. So, you are saying it will get initialized to a garbage value there in case 3?
No, it won't. I mean, the observation is correct, but uh, okay, let us say that even though it's initialized to garbage value, then your observation is correct, right? That case 3 and case 6 are similar, no matter whatever the value is at the vector location 6. If you see this thing will evaluate to vector of 6 and this thing also vector 6, I mean vector of 6. And so what we are doing is, whether id is 3 or 6, what we are doing is we are assigning it with vector of 6, and no matter whatever the value is, as long as we are doing it correctly, it's okay, right? So yeah, this is one observation. Case 3 and case 6 one can be combined. Is there any other observation that any one of you have? That is still one more, at least from my side. Please observe.
Like the ID is appearing in the equation, like initialization equations.
The 2 and 0 can be combined, right? Case 0 and case 2.
How can it be combined? Case 0, case 2. Case
Both
2
of
is
them are vector
yeah,
of ID.
please
Oh,
go ahead.
sorry.
Sorry.
Yeah, it is. I was wrong. Sorry. Sorry.
Yeah, I mean, case 0 is initializing it to 0, and case 2 is initializing to vector of 0, which are two different things according to me at least. Yeah, still one more thing is pending. Please observe it carefully.
But vector ID of ID minus 2 will be 2 minus 2, right?
No,
Sir,
4 and
case 8 or case
4
4?
and 8.
Yeah, sorry, one by one, I am unable to.
In the
I
case
think it is
2,
4 and 8.
Yes, that's correct. Case 4 and case 8 are same. If you see, this thing and this thing is similar. 4 plus 4 plus vector of ID is same as 8 plus vector of ID. So two things can be merged, at least from my side. Case 4 and case 8 can be merged. Yeah.
But isn't it?
case 2 and case 0, sir. If you look at case 2, it just says vector ID of ID minus 2, right? ID will be 2 there, so ID minus 2 will become 0 again.
Yeah, but as I told, okay, let us take this. You told that ID will be 2 and 2 minus 2 is 0. Okay, perfect. 2 minus 2 is 0. But we don't know what is there inside vector of 0. Vector of 0 might be a garbage value, let's say 10,000. So is it similar? Is it same? ID of 0, vector of 0 is initialized to 0 and vector of 2 is initialized to 10,000. Is it not same, right? It isn't same.
But that if we look at it, depending on order of which thread comes first, the values might be different. But in the end, we can only point to like a certain index marker.
I didn't got your question. Sorry. Can you explain it with some clear example?
Sir, I'm saying that depending on, say, for case 1, or scenario 1, vector ID 0 executes first. That way 0 will get defined in vector ID of 0, and then vector ID of ID minus 2 will become 2 minus 2, and it will point to that. But if it's a different order, means it will be different even in the normal execution.
Yeah, I got your thing. Okay. I think I was wrong here, and probably you people were correct here. So I got your point. So it's lockstep fashion. Lockstep manner of execution. So initially ID of 0 will be initialized to 0. So vector of 0 will be 0, and vector of here it will be 2 minus 2, which is 0, and which will be 0 again. Yes, you are correct. Yeah. So this case 2 and case 0 can also be combined. Correct. I missed this one. So in fact, we can merge three things right here. As if I have understood it correctly, we can merge case 0, case 2. Then we can merge case 3 and case 6. And then we can merge case 4 and case 8 also. So three mergings are possible here. So number of steps will reduce from 10 to 7, right? So now we can execute this switch, this entire switch construct in just 7 steps. If we do it smartly, then it will take 7 steps if we merge these cases, as I said earlier. And else if we don't merge, it will take 10 steps. Any doubts here? I'll just briefly go back to the chat. Wouldn't thread execution difference execution difference may mean vector of 0 and vector of 2 have different values? Okay, I guess as I explained, since threads are executing in lockstep manner, okay, let me go back to this. Right. So okay, so the switch case is executed with, first of all, this kernel is executed with 32 threads only. So and warps will execute, warp threads will execute in lockstep manner. So first of all, this will execute. So vector of 0 will become 0 by this will be done by 0th thread. So 0th thread is initializing 0th memory location of this vector to 0, and then when we are moving here, when this case 2 is true, by this will be done by thread with ID 2. what it will do is it will check 2 minus 2, which is 0, which is vector of 0, and vector of 0 is 0. Hence, at memory location 2 also we are assigning 0. So it is as good as this. So we can combine these two. I hope that's clear. Who asked that question? I hope that's clear. Jaya Raman here. In the end, we cannot guarantee the value in any index, only which index is selected for which thread. Is that we can, in the end, we cannot guarantee the value in any index. Yes, because everything is initialized to, I mean, by default it is garbage. So I guess you're correct. I mean, we can't guarantee what will be in the what index. I mean, because I mean, we are doing some arbitrary operations, right? So we just can't predict the final output. Yeah, what will be there in each index, we can't guarantee. Yeah, only which index is selected for which thread is that right? Yeah, that is correct. Value in any array location. So yeah, value in any location we can't predict because we are doing the arbitrary operation and we are also using the prior values which are garbage. So we can't just tell what will be the final values in each array location. That is correct. Yeah. Okay, so I guess everything is clear up till this point. If there are any questions, then please unmute yourself and ask, else I'll move on. Okay, I'll move on then. Okay, yeah. So again, let us try this example, which is probably the last one for today. Let's say again I have this kernel which is launched with 32 threads, which is 1 watt, and I have this if else construct which says that if id is less than 16, that is from 0 to 15, I print this inside it, and there is something called as global variable, which I'll explain what is that. And else if id is from 16 to 31, I'll print this else, and then there is this global variable. And now what is this global barrier? It's a synchronization point. Think of it as a barrier. So what is barrier? So whenever there is a barrier, all the threads will wait at that point until, sorry, I reiterate. So what is barrier? Barrier is a synchronization point. So unless all the threads have reached that this statement, this barrier, uh, any of the thread will not progress further. So let's say thread 1 has reached this point, but not, all other threads are still doing something else. So thread 1 will wait here until that all other threads reach here. And once every thread has reached here, then only they'll proceed. So I want each and every one of you to think that what is the output for this program? What will happen for this program? And what will be printed? In case if it is printed, what will be the printed? What will be the printed output? I'll wait here for a few seconds to try out. Let me quickly go. Okay, consider barrier as some arbitrary function. And
Sir, you are muted.
okay, I don't know when I just went to mute. Yeah, but this is a very interesting observation that what about threads that don't make into the if condition? So they'll keep on waiting forever. And that is the important thing. Inside if 16 times, okay. Inside if 16 times, and then program gets stuck. Perfect. Okay, I've unmuted myself. So let us try to understand it. I am happy that you people have tried, but okay, let us try to understand it. So as this is a synchronization point, and as we know that threads execute, I mean warp threads execute in lockstep manner, and we have launched kernel with one warp only. What will happen is all the threads will come here. They'll see that for only first 16 thread that this condition is satisfying. So all other threads from having ID from 16 to 31 will execute no, and first 16 thread having ID from 0 to 15 will start executing this statements which are inside this if. So first of all, they will print inside if 16 times. Then there will be a this global variable. So each and every 16 threads will keep waiting here for other 16 threads to come, and only if they come, only if they reach this point, other 16 threads reach this point, they'll move on. But they are never going to enter this if condition, right? So this 16 thread will always keep waiting here, and yeah. So this program will end into something called as deadlock, because these threads are waiting for some another threads to finish their these threads are waiting for some other threads to finish some task. So that is something called as deadlock, and we'll study this issue of deadlock more detail in upcoming lectures of synchronization, but this is for now. So one thing, okay, first of all, there is some noise from someone in. Please, can you mute? Excuse me, can you mute? Hello. Unless you have any questions, please mute. Hello. I guess that's from. Okay. Yeah, so waiting for something that will never happen is something sort of is called something sort of a deadlock, and we'll study this later as part of our synchronization lectures. So this is a typical example of a warp threads getting into a deadlock, or warp threads waiting infinitely for some event happening which can only be done by other threads. So this is a typical example of deadlock for warp threads, and I wanted to highlight this so that you people can understand like something like this can happen for warp threads also. Okay, so far any doubts, anyone? Quickly. Okay, I guess there are no doubts. Okay, if there are no doubts, I'll move further. Probably I'll just cover one or two more slides for today and then we'll stop. Okay. Okay, so till now we just saw the computational aspects of the CPU programming, right? So we completely saw through the completely went through the computation part. We saw how to launch the kernel, and how to launch the kernel using typical hello world programs. Then we also saw how to transfer the data from CPU to GPU. First of all, we saw how to allocate the data using CUDA malloc, and then transfer it using CUDA memcopy. Then we saw the typical program flow, CUDA program flow, like how we first load data from file system to CPU and then transfer it to GPU and then do computation and then bring it back. So all these things we saw. Then we also saw thread organization, which was the part of computation. And then we saw all those things that we saw in last lecture, like how to launch the kernel for huge data size, and what is warp and what is thread blocks, and what is the issue with thread divergence. And probably we today delve deeper into the thread divergence issue and saw a couple of programs. So that was our agenda for computational part. Now we'll move on towards the memory part, which is again one important aspect of GPU programming or CUDA programming. And we'll look a couple of things here. The first thing is that we'll see is like what is the memory hierarchy in the GPU. That we'll see first. Then we'll learn about what is locality and locality of reference and all those things. How the latency affects the overall computation of GPU. I mean, overall computation on GPU. Then we'll see something called as memory coalescing and array of structure of array, and all those things we'll be learning. And probably then we'll learn how to exploit shared memory that I mentioned in probably the previous lecture. And yeah, that's it. I mean, we'll learn all these things. And yeah, so let us start with memory. I'll just cover one slide for today, I guess. So this is the typical CUDA memory model or memory hierarchy of the CUDA or GPU. So at the lowest level, I mean, you can see that there is one. I mean, there are threads.
Sir, your slide is not shared.
Oh, is
I
it?
can see.
Can anyone
Oh.
confirm if slides are visible? Hello.
Yeah, slides are visible.
Okay, I guess if someone is facing the issue, then you can just log out and log in. So
Okay.
yeah. Okay, yeah. Okay, so for today we'll cover this slide and we'll stop here. So let us understand what is the typical memory hierarchy or CUDA memory model. So at the lowest level, we have threads here, and each of these threads have registers associated with it. So typically there are few numbers of, let's say, 10 or 20 registers associated with each of the threads, and access to this registers is very fast because it is per thread, I mean, allocated to one particular thread. And then there is something called a shared memory. Probably I highlighted this thing in previous lecture also, or yeah. So, and this shared memory is sorry yeah, so this shared memory is something which is per block. So as we saw in the previous to previous lecture, that there can be up to 1024 threads in a block, and each thread will have some chunk of something called a shared memory assigned to it. And yeah, so it is a per block memory. So again, there is something called as register, which is per thread, and then there is shared memory, which is per block. And then multiple blocks together forms a grid, as we know. I mean, we have seen this in thread organization part. And then at the lowest level, there is something called as global memory. And this global memory is nothing but the GPU's DRAM, or it is also called as video memory, global memory, as well as the GPU's DRAM. And if you people remember the things that we were doing, like let's say CUDA malloc and CUDA memcopy, all these things will allocate the memory here in the CUDA, in the global memory or the DRAM of the GPU. So this is the typical memory hierarchy of the GPU. And okay, so coming to here, I mean, coming to this points. So global memory is also known as video memory, and it is the main means of communication between host and device. As I told, host will transfer the data to the GPU's DRAM or this global memory. And one more point to observe here is that this global memory is common across all the threads and across all the grids as well. If here we have just one grid, but if there are multiple grids, then it is also common across all the grids. So if, let's say, two threads from different blocks want to communicate with each other, they can do it via this what I can say, they can do via this global memory. So it's common memory across everything, I mean, across the entire GPU, all the threads of the GPU. And it's a main mean of communication, data communication between host and device, as well as the multiple threads of, or across all the threads of the GPU. And its content is visible to all GPU threads, as I explained. But one drawback of this global memory is that its latency is very high. Typically, it takes around 400 to 800 cycle for a thread to access something which is inside this global memory. And this is actually a very high time. We'll see that there are lesser times for accessing other memories like registers and shared memories. And typical throughput is 200 Gbps, which is first of all, throughput is the number of instructions that can be done in a unit time. So here the number of instruction, number of tasks that can be done in unit time. So here task is something like reading or writing from the global memory. And so 200 GBs of data can be read in 1 second, which is the throughput for this global memory. And yeah, so that's it for the global memory. Yeah, the next two things are this texture memory and constant memory. So there are two spatial, these are two spatial type of memory, and speciality of this constant and texture memory is like, first of all, their size is very small. Size is just 12 KB and 64 KB, and they are read only. You can't just update the things that are written inside it once they are initialized. So they are just read only, and yeah. So typical bandwidth of this texture and constant memory are much higher than the global memory, like 4 times, like 800 Gbps. And one more thing to observe about this texture memory is it is some sort of optimized for 2D spatial operations. Like, let's say you have a matrix, which is a two-dimensional data structure, and that matrix is of size 100 cross 100, and we want, let's say we are accessing some element 3, 3 in that matrix. Then all the elements which are close to it, like 3 to 3, let's say 3, 2 will be close, then 3, 1 will be close, and all those things which are closely associated with that cell will be accessible very quickly if your matrix is placed inside that texture memory. So it is optimized for 2D spatial locality. So that is the part for the texture memory and constant memory. And the use of texture and constant memory is like they are used for storing some metadata. Like, let's say you have some data structure which is used for managing other data which is placed in some global memory or somewhere. And so texture memory and constant memory can be used for some storing some metadata, and it can give you some faster accesses for accessing that metadata and so on. So probably I'll stop here. We'll cover cover the details about registers and shared memory in tomorrow's, sorry, not tomorrow's, next lecture. But probably I'll stop here and we'll take some questions if you have any. Okay, how can we avoid deadlock? This is something we'll see in synchronization, but if you are asking for this particular example, yeah, so for this particular example, if you want to avoid the deadlock, then you need to write this condition in such a way that all the 32 threads finish this, assuming that kernel is launched with 32 threads, all the threads finish this. All the threads basically land inside this one particular condition. If they go in two different cases, then there will be deadlock. So if you want to avoid it, you need to write the code in such a way that this this till this statement every thread makes through. Every thread reaches this statement. So that's way. But further we'll study in the synchronization part that how can we avoid deadlock and all those things. Probably I'll wait here for questions. Okay, machine cycles. Where was the machine cycles? Okay, I guess you are telling about this cycle. Cycles are like CPU cycles only. The number of the time taken by CPU. Cycle is something defined by frequency. If you remember from our first lecture. So let's say you have 1 gigahertz processor, then its cycle length is 1 nanosecond, and that is how the cycle is defined. It's the chunk of work that a CPU can do in that one particular cycle, that one time unit. General question: can we launch a kernel within a kernel? Also, if we get CPU side parallelization like OpenMP, can we start two kernels parallelization? Yeah. So first question I'll take up. Like, we can launch kernel from the kernel, and that is possible. And I have also seen some of the some of the examples in which this thing is done, launching the kernel from the kernel. Yeah, so that is doable. Also, if we get CPU side parallelization like OpenMP, can we start two kernels parallel? Yeah, if you, CPU and GPU are asynchronous, right? I told this in second lecture, I guess. Like CPU and GPU are not the same device. So even if you have something, I mean, running in parallel on CPU, you can do some other task on GPU. That may be parallelization. I mean, that may be starting of two kernels or anything else. So I guess that won't be an issue. Or probably I misunderstood your question. If you think that way, you can just unmute and ask. Texture memory, constant memory is per thread block or per SM? Okay, so texture memory. Okay, I missed mentioning that. So texture memory and global memory is something. Sorry, texture memory and constant memory is something like global memory. It is across everything, across all the grids and all those things. It's not thread block or per thread or per grid or anything. It's similar to global memory. I mean, similar meaning it falls in the same place in the hierarchy as the global memory falls. So it is common across everything. Okay, is register memory the fastest? Yes, the register is the fastest one. Yeah, register is the fastest, and we'll see this how fast it is. And it's even typically faster than the shared memory. So something like this is there, like hierarchy is this. First of all, first comes the register, which is the fastest one. So thread will look into registers. Then thread can look into shared memory because it is faster than, I mean, it is faster than going to the global memory. So register, then shared memory, and then global memory. That is the order that we should go to reduce the latency, because fastest is the register, then shared memory, and then global memory. Okay. Yeah. Okay, I guess if there are no questions, then probably we'll end here.